let theta be the angle between two vectors. We're going to do v and w. And then we have a relationship between angle and dot product pretty quickly. We have the dot product of v and w is equal to the length of v times the length of w times cosine of the angle between them. And so I'm going to draw two little pictures here. One is going to be in here, and this is going to be the law of cosines picture. So law of cosines relates the length of the sides of a triangle to one of the angles opposite it. So I kind of think of it as this angle and the side across from it having a relationship. So if this is side A and that's side B and that's side C, law of cosine says that the length here squared, the far length squared, is equal to a squared plus b squared minus 2ab cosine theta. And I also kind of like to think of the law of cosines as how much a triangle fails to be a right triangle, right? C squared equals a squared plus b squared works when you have a right triangle, right? But when theta is 90 degrees, cosine of 90 degrees is 0, and all of this term goes away. Yeah, so that's a handy way to think about it. All right, why did I draw this picture? I drew this picture because over here we have two vectors, and they're going to form two sides of our triangle. And how do I have it here? I have v and w here. And here we have the opposite side, and that opposite side is actually v minus w. If we think about it for a split second. Why is this v minus w? Well, if I add w to it, if I put it at the end of w, I get v. Yeah, this vector, v minus w, if I add w to it, I got v. Perfect. And according to our assumptions, or hypotheses, the angle there is theta. And so, what can we set up right away from the law of cosines? We get to set up that the length of v minus w squared, that's c squared, right, is equal to the length of v squared plus the length of w squared minus 2, length v, length w, I don't want to run into myself, cosine of theta. And that middle part's a little hard to read. Let me see if I can get that good. 2, length of v. There's always so many little lines. All right. 2, length v, length w, cosine theta. All right, so does everyone see how I set that up? Yeah, more or less nods. This is the vectorized version of the law of cosines. All right, but we have down here that we have all these squares of lengths, right? Squares of lengths are, from our earlier viewpoint, just the result of dot product of a vector with itself. Yeah? So wherever I see that, I can replace with the dot product of the vector with itself. And here we have v dot v, right? Plus w dot w minus 2. And these are not squared, so I just have to leave them, right? That's going to be fine. We have them in here anyway. We see that they're going to come out. So v dot v plus w dot w minus 2, length v, length w, cosine theta. And now we're actually almost done with our theorem. We're really close. Number 4 is going to come into play on the left-hand side, right? I have v minus w dot v minus w. I didn't know how to deal with that before, but now I know I can FOIL. So let's FOIL. Yeah, FOIL the plans of the evil mastermind. All right, so what do we get here? What's our FOIL result? Yeah, you guys can answer. You guys can say it.
B squared minus 2WB minus W squared, or plus W squared.
Yeah, and it's squared, but I'm actually going to keep writing v dot v in this case. Yeah? Okay. V dot v. So minus what?
2V dot W.
2v dot w? Right. I can do 2v dot w because it's commutative. Nice. Plus w dot w. And that equals v dot v. Oops. I always have a tendency to want to write the v's as w's. Minus 2v w cosine. Cool. All right. A lot's going to drop out of this equation, right? Let's look for things that we have on both sides. You have the same thing on both sides of an equation, you can just cancel it. I'm going to be able to cancel this. I'll cancel it below since some of you are still writing. And I'll be able to cancel with that. I'll be able to cancel this with that. And both sides are multiplied by -2, so I can cancel a -2 from both sides as well. And what's left over is just going to be that and that, my friends. So what we have left over is v dot w equals length of v, length of w cosine theta. Now, everyone feeling good about that? Naughty and good? Okay, great. And not as in naughty, but naughty. Nodding. Yes. Okay. Other form of this, which you probably have seen even more frequently, is that cosine of theta is equal to v dot w divided by length of v times length of w. Quick question, why am I allowed to write it in that form?
You just divide the lengths.
Why can I divide the lengths?
That's the property about algebra. You just divide on both sides.
There is sometimes a problem with that property.
That's the lengths are just a number.
Lengths are numbers, but I can't divide by 0. Why do we know that they're not one of them at least 0, right?
Because there's no zero vector.
There is a 0 vector, yeah.
But it
yeah.
doesn't make sense to describe an angle between the zero vector and something else.
Right, that's a good one, yeah.
Because you're multiplying two norms on the bottom, which must come out positive numbers because you square each of the individual terms in
Right, yep.
normal numbers.
Yep,
not
and the
complex.
only thing I'm worried about is if one of these initial vectors had been 0. So I did actually not put in something that needs to be here. So both of those two vectors are not the 0 vector, right? Yeah. So just, we have to kind of be careful and pick through things. If one of them had been the 0 vector, right, there's no way to define the angle between one vector and a vector that isn't there. So we're okay to divide here, that's why, because we're dealing with two non-zero vectors. Nice. Everyone cool with that part? Yeah. Okay, so that is a relationship between angle and the dot product, and we use it all the time to find angles between vectors. One thing more I wanted to say too is it didn't really matter that we were in three-dimensional space here, right? We have like two vectors in 3D, right? It doesn't really matter. The angle between them is really kind of a two-dimensional property, right? We still only cared about the lengths of these two vectors and their dot product. So this defines angle between two vectors in any dimension. If we'd had, say, two vectors, each that had 5 entries, right? So for n-dimensional vectors, this holds. I don't know how to even draw a vector in 4-dimensional space, but because angle is really sort of like a 2-dimensional property, and we have a formula for it here, we just define angle between vectors of any dimension to be their dot product divided by their lengths. Yeah. Or you might prefer to call it a norm when you get out of the 3rd dimension. Yeah. All right, so we have all of that. the next most important thing is going to be projections. So is everyone good if I get rid of this side of the board? Cool. I don't think I'm going to be using this part of the thing very frequently. Well, actually, maybe I shouldn't say that. Maybe if we have, like, you know, to use the invertible matrix theorem or something, then I could write it over there and leave it there all term. Who here has seen the invertible matrix theorem? Who here can recite it by heart? No one. I can, don't worry. The invertible matrix theorem, if you haven't taken linear algebra, is a theorem with about 20 different equivalent statements in it. So,
There's part 2 also.
oh, there's part 2, my friends.
Like, for like 10.
As I say, I think at least the textbook we use here, I don't know if it's actually described anywhere in full.
Oh, really?
It's just, there's a bunch of.
There's a bunch of parts, yeah.
That describe different pieces of it, because they introduce, it has to do with different concepts.
When your proof goes from
Yeah.
A, B, C, all the way down to like U and V.
Yeah, you need numbers for it. There's more than 26 statements, I'd say. All right, so projection of one vector, we'll do V, quote unquote, along W. And is this all familiar? Raise your hand so far if this is familiar. Cool, good. Who here has seen projection of a vector along another vector? Great, all right, let's just review it real quick then. Recall the unit vector. Oop, go on. In direction V. And we're going to call that, or excuse me, we're going to write that as denoted E sub V. So if we have a vector V here, and it's longer than 1, this little vector that's right there, that is length 1 along that unit direction, is called the unit vector in the direction of V, and we're denoting it EV, and it's given, well, if I have a vector and it's some length and I want it to be length 1, I just divide by its length. So is given by EV is equal to the vector V itself divided out by its length. Yeah. And notice this is a vector and this is a scalar, so it might be more proper to say that this is the vector V times 1 over its length, right? Yeah. Cool. All right, and now the projection. Let's go ahead and draw another photo here. Not really a photo, I don't know what I'm talking about. That's definitely not a photo. So that's no longer going to be V. What is that? That's W. So say I have a vector V and a vector W, and I want to know like what the shadow area under here is. Yeah, I want to know how long that is. And I want a vector that's pointing that way, because maybe I want to write V in terms of one vector that goes along W and one vector that's perpendicular to it, as you will probably have done in things like the Gram-Schmidt process if you've taken linear algebra or other things of this kind. You might want to decompose this vector into the sum of 2 other vectors that are pointing in certain directions. Well, let's see. I feel like I know how to get a vector in the direction of W. That's the unit vector. So somehow I want to use my unit vector, right? So that's my unit vector here. Maybe this is EW, right down there. But then I need to get it a little bit longer, right? I need to multiply by some unknown thing here. Yeah. So this is the unit vector in the length of W, but I need to multiply it by something. And, well, we need to know what this something is.
Perpendicular?
Perpendicular, yeah. So this perpendicular here, well, we know from trigonometry actually how to find the length underneath there. It's given by what? The length here is actually going to be given by cosine of the angle between the vectors times the radius